Okay, class, welcome to week 7 of the course. And this week we are going to begin to get into inferential statistics, a very important topic where we move beyond the descriptive statistics that we've been working with. Uh, and we begin to make inferences with statistics and test hypotheses. So there are some basic concepts in inferential statistics that we want to establish here at the beginning. First of all, the definition of a statistic: any measure that is obtained by having measured a sample. So we talked about samples, where we take a small group from a larger population. And when we take a measure from a sample, we call that measure a statistic. So if we sample a group of people from this class and we measured their height and we took their average height, that average would be a statistic because it's a measure that is obtained by having measured a sample. Now remember that in order to make accurate predictions, we want representative samples. So if we were going to use a sample from this class to predict the average height of the class, we would have to sample people randomly and use the average statistic as a way of making an inference to the true population mean of height in this case. Now, whenever we draw a sample, there's always what we call sampling error. Sampling error is defined as, in this case, the difference between the sample mean, which is indicated here by the large M, minus mu, which is the true mean of the entire population. So sampling error is the difference between the sample mean and the true value in the population. It's very important to note that sampling error is not a mistake. It's not an error in that sense. It's not a mistake that somebody makes. It is error that arises from the fact that the sample is necessarily different than the population. So if I took 5 people at random from the class and calculated their height, their average height is necessarily going to be different than the true average height of the entire class if I measured everybody. That difference between the sample of 5 and the entire class is referred to as sampling error. You probably have heard this term sampling error in the context of political elections. When a sample is taken of the entire country and people are asked who they intend to vote for, you get a report of the percentages, and then we're usually told that there is some magnitude of sampling error built into that prediction. So there's always a difference between the sample statistic and the true value in the population, which for the mean is referred to as mean. It's not a mistake. It's necessarily something that exists whenever we sample from a large population. Now, bias is when we would have a constant sampling error in one direction. That's referred to as bias in the sample, and we'd have a sampling error that goes all in one direction. So, for example, Sprinthal talks about at one point he talks about the famous political poll back with John Dewey and Roosevelt, where they selected a sample that was biased. They got too many people who owned automobiles. They got it from the vehicle registration list, and these people were generally wealthier than the general population, and they tended to prefer a particular political candidate, in this case Dewey, and they made it. The Literary Digest made a bad projection of who was going to win the election. It turned out to be wrong. They had constant sampling error in one direction. So that's what we refer to as bias. When the sampling error isn't completely random, it's biased in a particular direction. Now, this concept of the sampling distribution is simply an extension of a frequency distribution, which we've already talked about. So we've gone over a frequency distribution of scores. A sampling distribution is a distribution of points similar to any frequency distribution of raw scores, except for the fact that each point represents a group's or a sample statistic, let's say the mean, instead of an individual score. So imagine that we go into the class and we take several different samples of 5 people and measure their height. We have now 5 different scores, but the scores in this case are now means based on samples of 5 instead of an individual score when we talked about a frequency distribution. The raw scores were just single scores. In this case, the sampling distribution, the scores are actually group means. And so that's what we mean by a sampling distribution. The mean of the sampling distribution of means, or the mean of means, is a grand mean. And I think at this point, Sprinthal says in the text, know what I mean, trying to make a pun out of this. But imagine that we have taken the class and we've gone in and drawn 10 different samples of 5 people, or all the possible samples of 5 people. We could do it with 6 people or 8 people, but we draw all possible samples and we calculate the mean of each of those samples. Well, the mean of that sampling distribution of means is a grand mean. It's the mean of means. That is, it turns out that that's the mean that we would get if we measured everybody in the population and took the average height. And so the mean of means, or the grand mean, is a parameter. A parameter is based on every element in the population, whereas a statistic is based on a sample from the population. So the true parameter mean, mu, in that equation that we had up there a few slides ago, that's a parameter. Mu is a parameter because it's based on every single element in the population, whereas the statistic is based on a sample. Now, just as there's a standard deviation of the sampling distribution of scores, the frequency distribution of scores, we computed the mean and the standard deviation. We can also compute a standard deviation of the distribution of sampling means. So imagine now we've taken all possible samples of 5 people out of the class and computed their height. We could compute the mean of each of those samples. We can also compute the standard deviation of the distribution of sampling means, or the average amount that a given sample that given sample means deviate from the grand mean. So imagine now we have all these possible samples that give us a mean. We can figure out how much they, on average, deviate from the true mean, the parameter, or the grand mean. And the standard error of the mean, or the true value of the standard deviation in the population, that is a parameter. We typically don't know what it is. So parameters we generally don't typically know unless we measure every element in the population. We don't know exactly what percentage of people plan to vote for Trump. We'd have to measure every single person in the population before we could come up with that parameter. Similarly, we don't know the true standard deviation of the sample means unless we measure the whole population to get that standard deviation. That's a parameter we typically don't know. So the formula for the standard error of the mean looks familiar to the formula for the standard deviation. If you go back to the formula for the standard deviation, it is the sum of the scores in the distribution squared divided by n over the mean squared, and then take the square root of it. This is a similar formula. It's the standard error of the mean. This is a parameter, and it's based now on means, not scores. So you can compare these two formulas in the text. So it's just an extension of the mean and the standard deviation that we talked about in frequency distributions. Now we're talking about samples of certain sizes. The formula looks similar. And now we are beginning to use inference principles. And I would draw your attention here to pages 163 to 165 in Sprinthal to go over this material and get clarity on it if my comments here don't give you clarity on it. And this is also going to be very useful for you in the written assignment, the final written assignment that you're going to do with football statistics that I will be going over at some point. But And I've got the spinning circle down there right now. For some reason, the slide is not advancing at this point. So let's just wait for that. But you might want to go to pages 163 to 165 in Sprinthal and take a look at those. We're now beginning to use inference principles. What do we mean by that? Well, we're taking a sample and we're making an inference about the population. And the first statistical test that we're going to talk about in doing that is called the z-test. This is not used frequently because we rarely know the parameter mean and the parameter standard deviation in any population of interest. We don't know those parameters. In the z-test, we have to know those parameters in order to do the test. But it's still helpful to introduce some of the conceptual terms, and you see what the statistical test is like. So in the z-test, what we're doing is we're using this to determine the probability that a given sample that we take is representative of a known population. So let's suppose for the moment that we actually knew the average height of everybody in this class. When we do the z-test, imagine we take a sample of, say, 6 people from the class, and we use that sample to determine the probability that this sample is actually representative of the entire class. That's the question that we're determining when we do a z-test. We're determining the probability that a given sample is actually representative of the known population. So I'm going to give an example here from media research. Suppose we know that the average home in our nation has 4.1 television sets in the home. Actually, that would be low. If you came into my home, I actually have 8 working television sets in my home. My excuse for that is that I am a scholar of mass communication, and so I have to have a TV set in almost every room in my house, lest I miss something important that's going on in the media. But let's suppose that we, that's a feeble excuse, I know. Let's suppose that we know that the average home in the nation has 4.1 TV sets. That is a parameter, that's the true mean in the population, 4.1. Typically, again, we don't know that information, but for the sake of the z-test, we're going to say we know it in this case. And we know then that the standard error of the mean, again, that's a population parameter. The standard error of the mean, the standard deviation of the sampling distribution of means is 0.80. Again, we typically don't know that. We're supposing for this case, for the example in the z-test, that we do know it. Okay, so we have a known mean in the population of 4.1 TV sets and a standard error of the mean of 0.80. That means that the average deviation from the mean for every sample that we draw, the average deviation is 0.8. So those are our starting points for this example. Now, we take a sample in Lafayette, and we find out that in Lafayette, the number of TV sets in Lafayette homes is 2.4. So we could do that in any variety of ways. Maybe we draw a random sample from the listed phone numbers in the Lafayette phone directory, and we call people up and ask them how many TV sets they have, and we record that, and we get based on the sample, we get that the average number of TV sets in Lafayette homes is 2.4. So based on our sample, our estimate of the number of TVs in the home is 2.4, not 4.1, which we know is the national mean. Now, the difference between our sample of 2.4 and 4.1, that difference could, again, just be sampling error. It could be that our sample, it could be that it's just it's not a mistake, it's just the difference that emerges from our particular sample and the national population. Or it could mean that our sample is not really reflective of the population of known mean 4.1. That is, it might be that our sample does not represent that larger population. The difference could mean that we have evidence that we're dealing with a different population, that Lafayette is so different from the national population that we ought to conclude that our sample really does not represent that population. It represents a different population. Well, we can determine that with the z-test. So if we're dealing with random error, if we're dealing with just sampling error, then the difference between our sample mean of 2.4 and the population mean of 4.1 is only due to chance, and we should accept the hypothesis that the sample mean is in fact equivalent to the population mean. Now, I don't mean equivalent in exact numbers, but I mean equivalent in the sense that the sample mean is representative of that population mean. It really isn't that. It isn't really different, even though it's different in magnitude. We would conclude that it is representative of that population mean of 4.1. And that hypothesis would be the null hypothesis, or the hypothesis of no difference. And we would represent that this way, that our sample mean, in this case 2.4, is equal to the population parameter of 4.1. That's the null hypothesis. M is equal to mu. We don't mean exactly equal in terms of the numbers, the magnitude, but it is equal in a rough sense in that the mean represents that population. If, however, we are dealing with a difference that is not due to chance or random error, but instead is due to a real difference between the sample mean and the population mean, then we should reject the null hypothesis and accept the hypothesis that the sample mean 2.4 is not equal to the population mean 4.1. And that hypothesis would be the alternative hypothesis, or the hypothesis of difference. And we would represent that alternative hypothesis this way: our sample mean is not equal to the population parameter mean mu. That 2.4 is not equal to 4.1. That's the alternative hypothesis. So now we actually do the z-test. Based on the information we have, we can compute a z-score, or a z-value, for our particular sample to see where on the distribution of sampling means we fall. So, remember the z-test formula. This was a raw score minus a mean. Now it's a mean minus the population parameter. So it's a sample mean minus the population parameter divided by the standard error of the mean. This used to be a standard deviation in a frequency distribution. It's now 0.80. We gave this as our population parameter standard deviation. So the z statistic boils down to this: 2.4, which is our sample mean, minus 4.1, which is our known population parameter mean, divided by 0.80, which is our known standard error of the mean, our standard deviation in the population. And the z-score ends up being negative 1.7 divided by 0.8, or negative 2.12. That would be the value of our z statistic. Well, once we have that, we can go to the z-table. So we go to table A in the back of the book, and we look up 2.12. In this case, it's negative 2.12, so we know we're on the left side of the distribution of means, and we find a value of 48.3%. That is, 48.3% of the distribution falls between a z-score of negative 2.12 and the mean. And now we have a decision to make. So we find that 48.3% of the distribution falls between a z-score of negative 2.12 and the mean. That means that the Lafayette mean for TV sets per home, 2.4, falls in the lowest 1.7% of the distribution, because 48.3% falls between the mean and that z-score. We now know we're in the lowest 1.7% of the distribution of sample means. If a z-score falls in the most extreme 5% of the distribution for a given z-test, then the conventional statistical rule requires us to reject the null hypothesis that the sample mean was equal to the population mean. That is, we are so far away from the population mean, we're in the most extreme 5% of the distribution, that we have to make a conclusion that this sample is not representative of that population. It falls so far away from the true mean that we conclude it is not representative. So we would, in this case, accept the alternative hypothesis that the sample mean is not equal to the population mean, and thus it probably reflects a different population than the one we know, the national population in this case. When we reject the null hypothesis and accept the alternative hypothesis, what we are stating is that there is a significant difference between the sample mean and the known population mean. So in this particular test, we're saying that the sample mean that we found in Lafayette is significantly different than the known population mean. Thus, the difference between 2.4 TVs per home and 4.1 TVs per home is a significant difference, not likely due to chance fluctuations produced simply by sampling error, but in fact, we're dealing in a completely different population. So that's basically the logic of the z-test, and there are some key notions here that you want to pay attention to. The result is statistically significant if it falls in the most extreme 5% of the distribution of z's. So notice here that we, just to put that back up again, notice here that we are in the most extreme 5% of the distribution of z's. When we did this test, we decided that we were in the most extreme 1.7% of the z-score distribution. So in this case, our z-test, our value of z, put us out into that zone where we would declare the result to be statistically significant. So just to get that slide back again, to get the percentage exactly right, yeah, we're in the most extreme 1.7% of the distribution, because we found from the z-table that 48.3% of the means fall between our mean and the true mean in the population. Okay, so, and that would mean that we have a significant difference. Now that logic of falling in the most extreme 5% of the distribution is statistically significant, that logic is true in every statistical test that we do. The z-test is the first test that we have introduced here, and it's the one you're going to be using for your final assignment, which again, I say I will go over with you before you have to do that, just to clarify what's going on and how it parallels what we've just done here. But these slides here in the lecture and those pages that I reference in SprintBall will be very important to you in figuring out the final assignment and working with that and setting it up correctly and doing it right. Things start to get a little bit more complicated here as we go into making inferences, but hopefully you can follow the logic. SprintBall's discussion will embellish what I've gone over here, and hopefully you will be able to comprehend this clearly. See you next time. That's it for now.